Hello, my name is Jihyuk, and I'm a PhD student at Université de Sherbrooke and INSA Lyon, supervised by Professor Sébastien Ponce, Dr. Benoit Michaud, and Professor Jocelyn Bonjour. Today, I'll be presenting research entitled Eulerian-Eulerian multiphase frost model based on phase change driving force. Before I begin this presentation, a quick summary of the presentation is that a Eulerian-Eulerian multiphase model employed based on non-dimensional phase change driving force with frosting criterion for the velocity and water vapor concentration will be presented, with the modified definition of the non-dimensional coefficient for the frosting condition, and the validation against the published experimental results will also be presented. Before I begin to introduce the problem, the frost generally forms on top of a surface at a temperature that is at below 0 degrees when it comes into a contact with humid air. Frost generally adds a thermal resistance to the system while reducing the heat transfer between the system and the surrounding bodies. And frost is generally a problem for many different industries such as air conditioning, refrigeration, automotive, and phase change materials. Therefore, many researchers have been trying to create a generalized model for the frost development. And these attempts generally falls upon three different categories of numerical frost formation models. The first category being without the consideration of the influence of the airflow, therefore predicting the frost growth itself only. And the second category is with consideration of the both frost and the humid air by applying an appropriate interface condition between the frost layer and the humid air. And the third condition, or the third category, is the considering the mass transfer between the water vapor within the humid air to the ice. Out of all these three categories, third category of the numerical frost formation model was chosen as it accurately predicts the flow field changes and the corresponding frost growth. So the main objective of the current presentation or the current research was to extend the works of Wu et al. And Fredzebian et al. Using the mass transfer frost model for a wider range of applicable operating conditions by extending the non-dimensional co-frosting coefficient B, which will be presented at our later slides. For the numerical model, solver ANSYS Fluent 2020 R1 was used with the Eulerian-Eulerian multiphase model, with the primary phase being humid air and the secondary phase being ice. Momentum, energy, water vapor component, and volume fraction equations were discretized by the quick method, while the pressure velocity coupling was done by the phase couple simple algorithm. The pressure was discretized by the second order discretization, and depending on the velocity of the cases, laminar or K omega SST model was used. For the interface heat transfer and momentum transfer, or momentum exchange, when used fluid momentum exchange coefficient and Rance-Marshall's interface heat transfer coefficient was applied. For the mass transfer rate, Wu et al. Defined the mass transfer rate based on Gibbs free energy and defined a term called phase change driving force, which is shown in the slides which is shown on this slide as the mass fraction of the water vapor minus the mass fraction of the saturated water vapor divided by the mass fraction of the saturated water vapor. Then, Fredzebian et al. Separated the frosting condition based on the mass fraction component and the velocity component, and demonstrated the results being less sensitive to the non-dimensional coefficient B, as you see in the frosting condition for both cases. For this current research, a modified definition of the non-dimensional coefficient for the frosting condition shown on the bottom of the slide has been used and tested and validated against the experimental results. For the geometric model, the domain shown here on this slide has been used with the velocity inlet on the left-hand side with the outflow on the right-hand side, with the cooling plate applied as a constant temperature wall at the bottom of the domain with the small adiabatic wall imposed in front of the cooling plate, and a symmetry condition imposed on the top of the domain to reduce the computational cost. Most of the compared experiments for the domain of the experiment, the height of the channel was between 100 millimeters to 300 millimeters. Therefore, the growth of the frost ranging from 1 millimeter to 3 millimeters did not impact the humid air far away from the plate significantly. Therefore, applying an appropriate height of the channel and symmetry condition at the top of the domain significantly reduce the computational cost while providing results that are sufficient enough and accurate enough for the comparison. For the geometrical model, rectangular mesh with cell size of delta x equals to 0.1 millimeter and delta y is equal to 0.05 millimeter were used for all validation cases and provided grid independent results. The time step independent results were observed for delta t is equal to 0.05 second, 0.01 second, and 0.005 second for cases with velocity of 1, 5, and 10 meters per second respectively. The current model was validated against a number of different published experimental results, such as that of Hermes et al., Nascimento et al., Li et al., Wang et al., and Chang et al., with the cooling surface temperature ranging from -4 degrees to -25 degrees, with the inlet air temperature ranging from 6 degrees to 30 degrees, with the inlet air velocity ranging from 0.7 meters per second to 10 meters per second. For this slide, typical model numerical results obtained from the current model has been presented. This typical example is that of the validation case number 12 against the results of Wang et al. The volume fraction distribution, temperature distribution at times equal to 3600 seconds are presented, as well as the air velocity distribution at times equal to 300 seconds, 1800 seconds, and 3600 seconds are presented. As you can see from the numerical results, there is a thin layer of highly dense frost that has been formed on top of the plate. And for the temperature of the frost near the plate, the temperature is relatively similar to that of the plate itself. For the air velocity, you can see that there's a local increase of the air velocity caused by the deflection of the airflow caused by the frost. And this deflection signifies from times equal to 300 seconds to 3600 seconds, and therefore the increase of the air velocities caused by the air deflection also increases. Therefore, there's an accurate prediction of the interaction between the humid airflow field changes and the frost growth, which is expected from the model that can be observed. This is the video compilation of the air velocity distributions from 0 seconds to 3600 seconds for the case of Wang et al. You can see that the frost grows continuously from 0 seconds, and there's an air deflection caused by the frost growth, and then the increase of the air velocity caused by the air deflection also increases as the frost continually grows. For the results are compared and validated for the frost thickness and frost density. For the frost thickness, the maximum deviation of ±18% were observed for the against the experimental results between times equal to 1800 seconds to times equal to 3600 seconds. For the majority of cases, and for Chang et al. Cases for the validation against Chang et al. Between times equal to 900 seconds to 1800 seconds. For the maximum deviation between the first half of the simulated time weren't measured, as the frost thickness is relatively low. Therefore, any small deviation between the numerical and the experimental results will be further signified or altered by the small value of the frost thickness. For the frost density, the maximum difference of ±25% was observed for all cases, except for case number 13 against the validation of Wang et al. With the maximum difference of 29.4%. This higher maximum difference was suspected to be caused by the low temperature difference between the plate and the humid air. Therefore, there might be a different phase change that occurs, such as condensation, which interferes with the current model. As the current model only accounts for the desublimation as the only phase change that occurs within the simulation, the low temperature difference between the plate and the air might cause condensation, which interferes with the current model. It should be noted that for Hermes et al. Cases or validation cases, the low temperature difference between the plate and the air can also be seen. However, this difference, maximum difference, was further signified for the Wang et al. Cases, as the velocity of Wang et al. Cases is at 5 meters per second, while for Hermes et al. Cases, the velocity is at 0.7 meters per second. Accounting for these errors or differences, the results were obtained with the absolute deviation of 18.3% and 29.4% for the frost thickness and frost densities respectively, which is an improvement over the reported deviation of 30% and 39% for the average frost thickness and frost density of Wu et al. Also, as you can see from the frost thickness and frost density values compared for the numerical and experimental result, you can see that even for the 29.4% difference of case 13, it still is within the reason of the simulated values. In conclusion, the works of Wu et al., and Afrezibin et al. Were extended for a wider range of operating conditions, and the modification was performed to the non-dimensional frosting criterion coefficient to extend the range of applicability of the current model. And depending on the air velocity, K-omega elasticity turbulence model was applied. The model was validated in terms of both frost thickness and densities against the published experimental results and showed appropriate difference and showed that the model provides accurate enough results. Model showed slight difficulty for the cases with low temperature difference between the air and the cold plate, for particularly below 25 Kelvin difference for the tested operating conditions. We also saw that for the difficulty, the difficulties is exacerbated for high velocity cases, while it's less significant for the low velocity cases. The model can be further improved by optimizing the definition of non-dimensional frosting criterion coefficient B. However, it requires significant efforts as all the tested validation cases has to be repeated with the varying values of the frosting coefficient, non-dimensional frosting coefficient values. And these are the references that are used for the current presentation. And that was my presentation for today. Thank you very much.